Okay, we show that this E, we show that E is subset of E is E E is subset of union or K of E and K's. Okay, K runs from 1 to infinity for all n greater or equal to 1. This we show. Okay. So E subset of union K runs from 1 to infinity E and K. Reverse inequality is trivial because each E and K for any pair of positive integers, E and K is subset of E. That's by definition. So we prove just this. E is subset of union K runs from 1 to infinity E and K. So let's choose any point in E. Let x belongs to E. We show that it is in some E and K. This implies f and x converges to fx because E is subset of fx and f and x converges to fx for each x in E, for each x in x. Okay. So that means then for any positive integer, then for all n greater or equal to 1, not k, it is greater or equal to 1. Greater or equal to 1, we can find there exists k greater or equal to 1 such that mod of fmx minus f of x is less than 2 power minus. This is your epsilon actually. For every n, we can treat 1 by 2 power. It's a positive number, so this can be treated as your epsilon. For every epsilon positive, I can find a positive integer k such that this holds fmx minus fx greater less than epsilon for all m greater or equal to k. So what does it mean? It means that our x belongs to E and K. Trivial by definition of E and K. X belongs to E and K for all, and this is true for all n greater or equal to 1. So which implies that x for some k and for each n. So that means x belongs to union over k. Union E and K runs from 1 to infinity for all n greater or equal to 1. So thus whenever x is in E, it is in the union. So therefore E is subset of the union E and K. E and K. K runs from 1 to infinity for all n greater or equal to 1. So this implies the equality because reverse inequality is trivial. Each E and K is subset of E. So E is equal to union E and K runs from 1 to infinity. So this means that since this E and K is it's an increasing sequence with respect to K, and the union with respect to K is equal to E, so we can write this as E and K. It increases to the, that's the definition, it increases the union E and K runs from 1. That's a notation actually. That's already discussed, which is equal to E. So A and K converges to it increases to E with respect to the limit K, not with respect to n. Okay, with respect to K, and this is true for all n greater or equal to 1. Okay. So this means that as we already proved the property of the measure, this means that outer measure, because each set is measurable, outer measure of E and K, it increases to outer measure of E. So it's already in some lecture, this has been already discussed in one of our lecture. E and K. It is again this limit is with respect to n, K, not with respect to n, and this is true for all n greater or equal to 1. Okay. Now since this convergence is there, so for each epsilon positive, I can find a natural number kn, because its convergence with respect to k, such that this holds. So let's choose any epsilon positive. Now let epsilon be any positive number. Now let epsilon be a positive number. Since mu of e and since mu of e, measure of e is finite, and since the limit of this is finite, actually it is finite. Since whenever limit is finite, then for each epsilon positive, since this limit is finite, so this is finite limit, and it is a limit of e and k. So we can find for each n, because it's true for limit is true for each n actually. For each n, there exists kn greater or equal to 1, such that mu star of e minus mu star of e and k is less than epsilon. I can choose this as epsilon minus 2 power minus n into epsilon. So because this is my choice for epsilon, and I will explain why I have chosen this as an epsilon. So mu star of this, actually it will be mod here, but since e, since this is this e and k is subscript e, so that means this is always a non-negative number. So we don't need a mod actually here. So this mu star of e minus this is less than epsilon for all. This limit is with respect to k for all k greater or equal to kn. Why I choose kn? Why I am not choosing this k naught? I can also choose k naught for each k greater or equal to k naught. So this is true for each n. So for each n, if I vary n, I can choose different. Suppose for n equal to 1, then for each epsilon positive, I can find k1 such that k greater or equal to k1 mu star of e minus mu star of e 1k is less than 2 power minus 1 into epsilon. Suppose say for n equal to 2, this limit is also holds for n equal to 2. So for n equal to 2, I can find k2 such that mu star of e minus mu star of e2k less than 2 power minus 2 into epsilon. Okay. So this is the case of mu star of e minus mu star of e and k is less than 2 power minus n epsilon for all k greater or equal to. This is our situation here now. Now I can from this epsilon I have to find a measurable subset f of p such that measure of p is measurable subset f of p such that measure of f is less than epsilon. Then I have to show that on e minus f, fn converges to f uniformly. So let's define that set f. Define f is equal to, it's equal to union n runs from 1 to infinity. Then I will take the difference e minus ekn. So those kn is actually e set difference minus ekn. Okay, not it's e and kn. Okay, so this is e and kn, not this is e and kn. So e and kn e and k. Let us define this f, and we see that this f is measurable and it is subscript p because it is the union of e minus e and kn. So it's always each so f is subscript each, f is subscript e minus e1 k1, f is subscript this e minus, because e minus you can say this e minus 1 k1 is subscript p, e minus 2 k2 subscript e. So if I choose the union, then union is obviously a subscript of e. So this f is actually subscript p. Then f is subscript p. Then f is subscript p, and also it's measurable because each e and kn is measurable. E is also measurable. Difference of two measurable sets is again a measurable set, and union of measurable sets is again a measurable set. And It is established and is measurable and is measurable. Now let's find its outer measure. Let's we show that actually its outer measure is less than epsilon. Let's find that outer measure of f, which is equal to outer measure of union and runs from 1 to infinity e minus en kn, and that's equal to we can say this is less or equal to using countability subadditive property. It is summation and runs from 1 to infinity mu star of e minus en kn. That's equal to summation and runs from 1 to infinity. What's mu star of difference? It's difference of the mu stars. It has been already discussed. This is mu star of e minus mu star of en kn. That's this sum of these two. Let me go right here curly brackets. Okay, now this one mu star of e minus mu star of e and kn is less than epsilon times 2 power minus n. So this is less than summation n runs from 1 to infinity epsilon times 2 power minus n, and this is equal to epsilon times summation n runs from 1 to infinity 2 power minus n, and that series is equal to 1, so it's equal to epsilon. So thus mu star of f is less than epsilon. Thus mu star of f is mu star of f is less than epsilon. It's less than epsilon. Now we show that on e minus f, fn uniformly converges to f. So let's prove that. Let's prove that on e minus f, fn converges to f uniformly. So let's choose the point x belongs to e minus f. Okay, let's choose this. So what's this? You can easily verify this. This is equal to the intersection using the value of f. You will see this is equal to, and using De Morgan's law, you can easily verify it. It's not too hard. It's a simple exercise for you. So you can easily verify this. This difference is equal to the intersection n runs from 1 to infinity e and kn. So this can be easily done. E and k. So x belongs to the intersection, which implies that x belongs to each. That means x belongs to E n kn for all n greater or equal to 1. But whenever x is in E n kn, this by definition means mod of fmx minus f of x is less than 2 power minus n for all kn, where this kn is greater or equal to m. Sorry, is it k? Sorry, it is. I think it is. Its definition is for what's the definition of e and k? It's m greater or equal to k. M is greater or equal to k. So here k, our k is here kn. So m is greater or equal to kn. M is greater or equal to kn. For all m greater or equal to k. For all m greater or equal to k. This holds. So this proves fm converges to f uniformly, and this epsilon, you can see here epsilon. You can see this kn for each epsilon positive. I can choose n sufficiently large such that epsilon will be less than or 2 power minus n should be less than epsilon. So I can choose here this epsilon which is such that fmx minus fx will be less than epsilon. So I can choose n sufficiently large such that 2 power minus n is less than epsilon. That's very simple. But here, this is our kn, and you see this kn is independent of x. It does not depend on x. So that's for the requirement. That's the requirement for the uniform convergence actually. If you will see the construction of kn, it does not depend on x. It's independent of x. So this means that fm converges to f uniformly on e minus f, on e minus f, because this x was chosen in the set e minus f. So that proves this theorem completely. So finally, I will give some exercises for you that you will do. This is the exercise number 1. X as I'm using fixed measure space, and f is a function. Let f be a function from x to r. Let f be a function from x to r. Then show that f is measurable, and a is a dense subset of and a is a dense dense subset of R, like Q is dense in R. Its closure is whole R, dense subset of R. Then f from x to R, then where x is a measure space, okay. Then f from x to R, then f from x to R is measurable, is measurable if and only if the set x such that mod of fx such that don't use mod here, you can directly write this without mod. So that fx is greater or equal to a, where this a is in R. This is measurable for all a in R. Sorry, for all a in A, not R. For R, it's the definition actually. Yeah? If I use R here, that's the definition of measurable set. So for all a in E, if A is in R, then by definition f is measurable. Okay, but you have to prove that you have to restrict those constants. You will say if those constants belongs to the dense subset of R, then still the function f is measurable. That means from A belongs to A, you have to show that this is true for each A belongs to R, where A is dense. If this is measurable for each A belongs to A, you need to show that this is measurable for each A belongs to R. If you will prove that, then you can see this. Then you can say this f is a measurable function. That's what you need to show actually. Then show that. Then it says here. Then show that. Then show that f from x to R is measurable if and only if this set is a measurable set. So one more exercise for you. So I hope you will do these exercises. Give an example of a non-Lebesgue measurable function f from R to R. Give an example. Give an example of a non-Lebesgue measurable function from R to R, real line to real line, from R to R, such that mod of f is measurable. Its mod is measurable, but f is not measurable, such that mod of f is measurable. And you know that if f is measurable, then mod of f is measurable, but converse is not true. That's an exercise for you. You have to show that converse is not true. Mod of f is measurable. Mod of f is measurable. And not only this, there's one more property, and you see that f inverse of singleton set is always measurable in that case. F inverse of and f inverse image of a singleton set is measurable here. Is measurable is measurable for all a belongs to for all a belongs to. Okay, you had to show that this you had to give an example of a function which is measurable, such that mod of that function is measurable, but f is not measurable, and still the inverse image of singleton set is measurable, but f is not measurable in general. In general means inverse image of every open set need not be measurable, or every closed set need not be measurable. Only the inverse image of those closed sets which are singleton subsets they are measurable. Inverse image of each closed set is not measurable. And for mod f, you have to show that you have to show that inverse image of every closed set is measurable. But for f, the inverse image of every closed set need not be closed. That's what you have to construct. You have to construct a function f from R to R, which is not measurable, but its mod is measurable. Similarly, we have one more exercise. You can see this exercise. Let f be a differentiable function from R to R. That's very simple. If you really know the limit process of differentiability, if you really you have to apply the ab initio method of differentiability here, and you have to see this. F is a function from R to R, be differentiable, be differentiable function. So just apply the differentiability, the first principle. Okay, let's apply the definition of differentiability here. Okay, after differentiable function from R to R, show that f dash is Lebesgue integrable. Oh, that's very interesting. Show that its derivative is always Lebesgue measurable. Is Lebesgue measurable. And this is but this result is not true for continuous function. But I mean to say that if f is a function from R to R which is differentiable, then f dash need not be continuous. So here is an exercise. Give an example of a differentiable function from R to R. Give an example of a differentiable function f from R to R such that f dash is not continuous. F dash is not continuous. Derivative is not continuous, but derivative is always Lebesgue measurable. That's this exercise. Okay, that's the end of this lecture. In the next lecture, we will discuss step functions, and then we will discuss the integrability of step functions. Thank you.